Hi everyone, I was actually planning to make a single video on over-discharge protection, but I didn't want to withhold any information from my dear viewers, and that resulted in a rather large video. So I divided into three parts. In the first part, we will just talk a little bit about batteries, how you can power your microcontroller projects with batteries, why over-discharge happens, and why batteries gets unbalanced in series packs such as this one. And in the second part, we will talk a little bit about the internal fixed voltage reference on microcontrollers and how you can use it to measure the supply voltage, especially in microcontrollers like this with a wide operating supply voltage range. And in the last part, we will just write some code to implement over discharge protection and fix our spooky pumpkin here seems to be murdering batteries now. In this video, I will talk about over discharging batteries and why you shouldn't do that unless you hate batteries for a good reason. We will also write a few lines of code to show how you can implement over-discharge protection in microcontroller projects. So why am I holding this? Because this is a motion-activated jack-o'-lantern project I did before Halloween. I also did a post-mortem on it to see what could be improved. And one thing that became apparent in that post-mortem was, aside from being cool and spooky, this thing is also a murderer of batteries. I used three rechargeable nickel metal hydride batteries to power it, and it just kept over discharging them, and in the second batch even reversing the polarity of an unlucky cell. Link to this project's video and the postmortem are down in the description below. If you haven't seen them, it's useful for you to understand what's going on here. Unfortunately, this is also what a lot of low-end consumer electronics do to rechargeable batteries. Some of them don't give a shit, and some of them will slap a label somewhere such as "don't use rechargeable batteries." The moral of the story from a consumer point of view, keep an eye on your rechargeable batteries and take them out as soon as you notice the device they are powering starts acting odd. Before we fix this problem with software, let's talk a bit about batteries and why overdischarge happens. So batteries are chemical power storage devices providing juice for all sorts of things. They come in all sizes and shapes with different chemistries, voltages, and discharge rates. The voltage across the terminal of each cell when it's not providing power for a load is called open circuit voltage. Although this voltage will drop under load in different ways for different chemistries of batteries, it's a good enough indicator to decide whether the battery is good to go or depleted. Different types of batteries and chemistries have different cell voltages when they are fully charged. This voltage also changes with the brand and make of battery as well as how degraded the battery is. So you can assume each battery is slightly different like people, and we can only use rather loose ranges instead of absolute values when navigating the battery territory. For example, common nickel metal hydride cell has a nominal voltage of 1.2 volts. When fully charged, they will be at around 1.4 volts, but I have seen batteries with 1.3 volts, 1.5 volts, hot off the charger. These are all nickel metal hydride batteries, so it's quite hard to tell, but they will be usually around 1.4 volts. And it's different for other chemistries, such as alkaline batteries are about 1.5 volts, but fresh alkaline batteries can go as high as 1.6 volts. For lithium chemistries, again, when they are fully charged, they can go up to 4.2 volts. As the cell discharges, the open circuit voltage will drop. Generally speaking, the lower the voltage, the lower the juice left in the cell, but again, every chemistry behaves different and this relation is never linear. Each type have their own curves for state of charge versus voltage. For example, it's easier to tell the state of charge for lithium batteries looking at the cell voltage, while it's not so much for nickel metal hydride batteries where the drop in voltage is more sudden than gradual. But for each type, there is a minimum voltage where it's considered the battery is completely depleted. We shouldn't get close to these values because for rechargeable chemistries, it will speed up degradation, and in some cases it might just kill the battery, as in you won't be able to charge it or it won't be able to hold charge for long. For non-rechargeable chemistries, it's a bit more forgiving since depleted batteries are disposed, but even then, overdischarge can cause leaks, especially in series packs, and corrosive electrolytes in the battery will ruin your battery contacts or device. The other side to this story is discharge rates and current, as in how much power can the cells provide, but that's another story for another time since voltages
are all we need for over discharge protection. Now we have covered the voltage front, let's bring the thing, aka whatever is to be powered by batteries. Most devices such as processors, sensors, servos, etc., which you might be using in your Maker project, require different voltages such as 1.8 volts, 3.3 volts, 5 volts, 6 volts, 12 volts, etc. Usually you will need multiple power rails with different voltages, and some devices are okay with wider ranges such as the PIC10F that we have used in our jack-o'-lantern. And when we look at a single cell, fully charged or at its nominal voltage, the ranges could be completely different to what our device needs. This is another area where lithium cells shine and took over the market, since a single cell can power 3.3 volt, 1.8 volt devices. But even then, with more demanding things such as robots, power tools, etc., you will need more than a single cell provide. One solution to this is to use switching regulators to boost the voltage and increase the current consumption, but it's almost always simpler and cheaper to add more batteries and drop the voltage later with a linear or switching regulator. For low power devices consuming below 500 mA, linear regulators, especially low dropout ones, can get really close in efficiency to switching regulators and providing a very clean output. Now let's move towards our project to solve this problem. The jack-o'-lantern requires 3.3 volts and we want to power it with AAA batteries, either nickel metal hydride or alkaline, with a maximum voltage of 1.5 volts for each cell. We can add another cell in series that will give us a maximum voltage of 3 volts, but even that is not enough. So let's add another one. When we connect 3 cells like this, we will get a maximum of 4.2 volts for nickel metal hydrides out of this pack. In case of alkaline, it will be a little bit higher, but it's going to be close, could get as high as 4.8 in case of alkaline batteries. For both chemistries, it's safe to assume a single cell will be able to provide usable current down to 1.1 volts without getting over discharged. We can possibly go lower than 1.1 volts with alkaline batteries, and these ranges will leave some unused juice in them, but we primarily want to support nickel metal hydride batteries without over discharging them. So these ranges are good. Also, the sensor in our device requires at least 3.2 volts to operate properly. In summary, our battery pack will be providing a range from 4.5 volts down to 3.3 volts safely. But our thing does precisely require 3.3 volts, and 4.5 volts will damage it. So in this case, we will pop in a regulator to keep the voltage at 3.3 volts regardless of the input voltage, as long as it's within its limits. Now when we start operating this device, as the battery is discharged, the total voltage in each cell will drop. And we know for nickel metal hydride cells, 0.9 volts is the minimum. We shouldn't get near that. But in real life, batteries don't discharge nice and equally like this, especially when they are in series. They discharge more like this. And the imbalance depends on the internal resistance of each cell, how degraded its electrode, etc., and where it is in the pack. In this case, once we dip below minimum voltages, the stronger cells will start reverse charging the weakest cell. This will certainly reduce the lifetime of the cell and might cause irreversible damage. This is how our jack-o'-lantern murders its cells. In case of non-rechargeable batteries, this is what could cause leaks and ruin your device. For the lantern, we have used a fixed voltage low dropout regulator. The dropout on our regulator LE33CZ for the currents we are consuming are about 0.2 volts. As long as the regulator sees 3.5 volts on its input, it will provide regulated power at 3.3 volts. For some reason, I was assuming it will shut down magically when the input is lower than 3.3 volts, but that assumption was absolutely wrong. When the input voltage reaches below 3.3 volts, the regulator just does its best to provide a voltage as close as to the input. It won't be at 3.3 volts, there will be a dropout close to 0.1 volt, but it will keep operating and it will allow the over discharge to happen. With our lantern, it's fine if we stop somewhere above 3 volts behind the regulator. In that range, our motion sensor will still work and we are above the minimum voltages of our battery pack with some slack. Now let's have a quick look at the lantern schematic and see what options we have to implement a cutoff voltage for over discharge protection and reliable operation.